Okay, so we continue chapter 2, ET111B. So we're starting to look at how we deal with the operations, multiplication and division, when using this powers of 10 form. And you can see, from this example, again, we combined the exponents just by simply adding them. 4 plus 2 and 3. Whenever we move a value from the denominator into the numerator, we change the sign. So 6 minus 3 leaves us with 10 to the third. What's 10 to the third? 1,000. What are we going to find out later? That it's the metric prefix of K. It's all tools that we need to become electronic engineering technicians, okay? So don't get frustrated with it. Just keep working with it. Be mindful of all of these tools now that you are building into your tool chest for handling each of these different situations. Okay, a little more complex. 10 to the minus fifth, 10 to the third, 10 to the minus 2. So we combine our exponents in the numerator. Don't do anything with the denominator yet. This one's going to be pretty simple. I mean, this one you could look at. It's called by inspection. By inspection, 10 to the minus 2, 10 to the minus 2 is 1. They both cancel out. So we have 10 to the 0 if we want to go the long way around and actually do the math. But if it were me and I got to this point, I'd go by inspection, it's 10 to the 0, 10 to the 0 is 1. On this next one, again, combining terms, 3 plus 4 for the exponent, minus 2 plus 6 for the exponent, simplifies to 7 and 4. I pull that 4 into the numerator, 7 minus 4, 10 to the third. That's going to give me 1,000, or the metric prefix of K. We arrive, at this answer to be 10 to the minus 6 because the numerator can be written in powers of 10. I hope that you're seeing this, that these are quick ways for you to look at a problem and quickly ascertain what the answer is. There's nothing to do in the numerator. Everything is in the denominator. Combine your exponents, switch it to the numerator. Now we have a value that will later become a metric value of micro, 10 to the minus 6. Okay? We can look at it if we want to expand it out and say, well, 1 I know is 10 to the 0. If I do the full math on it, 0 minus 6 gives me 10 to the minus 6, and I'm at the same place. Okay? It's all the tools that you are building to help you understand how these values are. 10 to the minus 6 is going to be, like 10 microamps. You're going to find out that these are things that you're going to use all the time when you're calculating your values and doing your labs, when you need to calculate very small amounts of current. 10 to the minus 6. That's like, a soda straw compared to what's coming out of your wall socket. Rule 2-9, whenever a power of 10 form is in the denominator, it can be moved to the numerator by changing the sign. And we've seen that already. There it is. There it is. Okay? Get used to it. Convert the number to powers of 10 notation with positive exponents. Okay? So now what we're going to do is start moving that decimal point around so that we have values that make sense, values that are easier to work with, especially when we start doing multiplication and division. So we have a value here, 470. I can make that a decimal value by moving that decimal point from where it currently is behind the 0. It's understood to be sitting right there at the 0. To make it, by moving it one time, now I'm at 10 to the first power. I move it another time, I'm at 10 squared. I move it another time, I'm at 10 cubed. I move it one more time, move it on the other side of the 0 here, and I'm at 10 to the fourth. It may seem like something that, it's like, why do I even bother to do this? You're going to find out later. It helps you solve problems. It helps you deal with values of resistance and current and voltage when you get used to handling the exponents this way. Okay? You can do it the way it shows here, the same as, but look how cumbersome that is. You might want to, you might sometimes want to be doing this in your calculator. It might be tempting, but if you get used to using the exponentials, you can simplify your processes so much easier by just dealing with the exponent and moving that decimal point. As we make the exponent more positive, the decimal point then moves farther to the left. Rule 210 says for each place we move the decimal point to the left, the exponent increases by 1. Well, we saw that up here. 1, 2, 3, 4. Decimal point. Boom, 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 boom. Rule 211, for each digit we make the exponent more positive, the decimal point moves one place to the left. Okay, all tools. Okay, same thing here, converting numbers of powers 10 with negative exponents. Now we've got 470, but let's say for some reason I want it to be an exponent of -1. Add a 0, multiply it times 10 to the -1. Add another 0, 10 to the -2. Add another 0, 10 to the -3. It seems like a waste of time, but when you start dealing with these in terms of components and electronic calculations, this becomes very, very helpful tool. So if you look at Rule 212 and 213, again, the opposite of what we saw in the others. As you start moving that decimal point, the values of the exponents start decreasing by 1, i.e., the negative value is making it decrease. As we move the decimal point to the right, the exponent becomes more negative. As we place, for each place we move the point right, the exponent decreases. Okay, so look at these examples: 470, 4,700, 4,700. Okay, this is a squared value. Okay, we square these values and we end up with exponents that decrease in value by 1. It just takes practice. Sometimes you just have to pull out a piece of paper, scribble it down on the piece of paper, and prove it to yourself that this stuff actually works. Scientific notation. Scientific notation is the overall notation that we use to handle these values and make them easier to move. The subset of scientific notation is engineering notation. Engineering notation is the common notation for electronic engineering. You have to get used to using engineering notation that uses factors of 3 instead of the even factors 2, 4, 6, 2, 4, 8, or whatever. They're just not used in electronics. It doesn't make any sense. It doesn't match the values that we normally use in calculating and in components in electronic engineering. Rule 214, to express numbers greater than 1 in scientific notation, count the number of places the decimal point must move to the left. Okay, so if we want to express in scientific notation rounded to 3 significant figures, you got to get used to this. Significant figures are what becomes the basis for your accuracy in solving the problems and making sure you don't have a number that doesn't make any sense. Sometimes 7,064,832 doesn't make any sense. Sometimes it makes more sense to round it up. So in this case, since the 8 value to 3 significant digit is telling us to round this up to 765, we do that. Okay, 765 then is equal to 7.65 times 10 to the 5th. How did we do that? Well, there's an understood decimal point right here after the 0. 1, 2, 3, 4, 5. So we've moved the decimal point 5 places. Now we're at 7.65 times 10 to the 5th. But we have to remember that what we did here was we rounded with an accuracy only to 3 significant digits. Okay, without that, you don't know how accurate your number is. If you were to calculate something with an amount of current and you were off because your significant digits weren't correct or you weren't mindful of them, you'd blow up the circuit. You might burn the house down. So keep that in mind. Rule 215, to express numbers that are less than 1 in scientific notation, count the number of places the decimal point must move to the right. So now in this one, all of those leading zeros, it's like, oh, they give me a headache. Okay, let's get rid of those zeros. So let's move that decimal point. 1, 2, 3, 4, 5. We're going to put it right there between the 8 and the 7. And we're going to add, since we moved it 5, a -5 to denote that we moved it to the right 5 places. And now we have rounded to 3 places, 8.71. Notice we went from 6 here, getting rid of that 0, 3 places, 8.71 times 10 to the -5th. But we're mindful of the fact that we rounded this, we moved the decimal point, and we made it to 3 places. Rule 216, to add or subtract numbers in powers of 10, the exponents must be the same. So notice we're adding here. We cannot add these together. Now I can convert them to standard form, the big old numbers, 3 times 100, 4 times 1,000, gives me 300, 4,000, 4,300, and then I can convert it back to 1,000 by 10 to the third, and we've got a value that later I can say, well, that 10 to the third is the metric prefix k. 216, to add and subtract numbers in powers of 10 form, the exponents must be the same. Okay, for each digit we make the exponent more positive, the decimal point moves to the left. So let's look at this. 3 times 10 squared. I can move this over 1 place, add 1 more 10 to it, manipulating it to make it easier, where I can add then values that have a 10 cubed in each of them. For what we saw, it's this same problem that we saw in the previous slide, and now we end up with the same value. We manipulated these so that it was easier to handle. What if we want to subtract 6 times 10 to the -3rd from 10 to the -2? Okay, again, we manipulate the subtrahend, we manipulate that exponent so it's 0.6 times 10 to the -2. I'm going to move the decimal point that's understood right there after the 6, 1 place forward, and now I have 10 to the -2. Now I can add them together because my exponents are the same. And now I end up with 4/10 times 10 to the -2. Okay, then I can convert it if I need to back to the -3. You can check your work by performing the subtractions. Okay, so in this case, 1 times 10 to the -2, 6 times 10 to the -3, I convert them to pure decimal form. I do the subtraction and then I convert it back. So 1, 2, 3, that gives us 10 to the -3 times 4. Sometimes a ballpark answer is all that's required. In electronics, many components, i.e. resistors, and sometimes capacitors, are rated with tolerances. 0%, 5%, 10%. You're going to see it as you go along in your education to become an electronic tech, that those values become important because they're going to give you a range for the value of the component. Okay, so for most electronic and computer related problems, you can really use an estimate to solve for your answer. Okay, so we got the little squiggly line here that we use for the equals. That's telling it's equivalent to or almost equal to. Okay, so in this case, we're saying I'm going to take 3752 and I'm going to round it up to 4,000. And I'm going to take 8,439, since in this digit right here, the 4 is less than 5, and I'm going to round it down. So now I have two values that are easier to deal with, 4,000, 8,000. Okay, I can combine them together and come up with an answer that is reasonably close for electronics. Work through this problem, take a look at the estimations that we do, and you will see how this becomes a good tool and a good measure for for handling electronic calculations. In this case, we've got a problem here that we're going to calculate the indicated addition. Okay, so we've got a numerator and a denominator that's got exponents and values all over the place. So what I want to do is I want to simplify the numerator by using some estimated values here. So we estimated this so that we had 80 or 75 times 10 to the third, which is 80 times 10 to the third, and I'm going to make it 8 times 10 to the fourth by moving the decimal point. I'm going to combine my terms in the numerator or in the denominator now. I have to change my values of the exponent to make them the same. I can add them. Now I have both the numerator and the denominator as an exponent of 10 to the fourth. In essence, they cancel out, and I'm left with 5.03 divided into 8, 1.64. Okay. Same thing here. The example follows the same way. This was the example out of your textbook. Okay, one of the problems. Work these problems out. Make sure that you prove to yourself that they work, and then, sleep on it. You'll have the process down. A key point. Now we're looking at reciprocals. A reciprocal is nothing more than taking the value that's in the denominator and moving it into the numerator. With exponents, we move it into the numerator, we change the sign. The positive 3 becomes a negative 3. And now it's easier to work with. The reciprocal of 27.37 times that 10 to the minus third, I can make it closer to a whole number by moving that decimal point over, and I end up with 10 to the minus fifth. Okay, so the process of using reciprocals, again, sometimes you have to make the denominator a lot simpler. So we simplified the denominators here, as you can see here, and then we can invert it into the numerator, and we end up with our final answer. Okay, it's all a matter of dealing with the exponents. 217, when raising a power to a power, multiply the exponent. So now we're multiplying. We're not adding, we're multiplying. Okay, so 10 to the third we know is 10 cubed. If I square 10 cubed, I end up with 10 to the third times 10 to the third is 6. Well, I could very simply do that by multiplying the 2 and the 3 together. Okay. Sorry about that. Let me go back here. Okay, so dealing with the signs becomes a little bit of an additional measure. We have to keep track that we are, in fact, making sure that the signs, a negative, and a negative is going to give us a negative. Okay, this is going to give us a positive. This is going to give us a negative. So we have to learn how to handle those exponents when we're adding and subtracting versus multiplying and dividing. The other side of that is the square root. Start with the square root. We'll move into the cube root, but square roots are very common in electronics. If I have 10 to the fourth represented under the radical, I can say the same thing is 10 to the fourth to the 1/2 power. You'll notice that this simplifies to 10 squared because I can divide 2 into 4. If I'm dealing with a cube root, in this case, 10 cubed to the cubed root, then I have 10 to the third divided by 3, multiplied by 3, I end up with 10. So you can see it's just ways of handling numbers, dealing with the manipulations, but it takes practice. Final example here, we've got a square, 14.7 squared. We end up with an exponential value here of 2.16 times 10 squared. Okay, so again, ways of simplifying, making sure that we're using our significant values, our significant digits and figures, so that our numbers become reliable and something that makes sense. The square root of a number then is one of its equal factors. The square root of 100 then is a 10. So this just is showing you, if I take the square root of 100, it's the same as the square root of 10 of 10 squared is 10 times 10. One of the 10's factored out. I'm left with 10. Okay, so chapter 2 was a whole session here. We can go back to dealing with powers of 10. Next, we'll look at chapter 3.